The motivation for convolutional neural networks is coming from image processing. And for this reason, the typical data you have in a convolutional neural network is organized in the form of a three-dimensional matrix. And the three dimensions are the width, the height of the image, and then on the third component you have the number of channels. For example, think about it as the RGB channels in the original image, or then it could be the number of filters you have applied in the previous step, and this could evolve as you go through the processing of that image. So the way to see this data, and by the way, these matrices are also called volumes, or they are also called in machine learning tensors. So the way you could see this is that, for example, in the input you would have, let's say, a 32 by 32 image, and this image has in fact three channels, the RGB channels corresponding to red, green and blue. And so the original data you would have, for example, it could be 32 by 32 by 3, and obviously this could be different if you deal with larger pictures. Then you have maybe more than 32 on width and on height. And on the first step of a analysis you do to such an image, maybe you would like to apply some filters, and let's say that you apply 6 filters, and let's say that the result of each one of these filters is going to be a rectangle which is just slightly smaller inside. Maybe it's something like 28 by 28, and you have 6 such squares, one for each filter that you are applying. So 4 and 5, and here is the last one. So the result of this transformation in the first step, for example, it could be 28 by 28 by 6, and obviously this depends on the application you make. Maybe you do less filters or more filters, or the filters are going to produce different size of the square. This is just an example. Now, the point is that if you would like to process this with a neural network, you would have to have in the input layer, you would have the input layer, if this is input layer in a typical fully connected neural network, you would have to have as many neurons in this input layer as you have data points in your data. And in your data you have 32 times 32 times 3 values for your image, and that makes this is equal to 3072. So in the input layer you would have to have 3072 neurons. And then in the first hidden layer of your network you would have to have as many as you have as a result of these 6 filters. And so this is the hidden layer, and you would have to have as many neurons as you need to store all of these 28 times 28 times 6 values. And this 28 by times 28 times 6, this is equal to 4,704 neurons. And then you build these connections, and the thing is that in a fully connected layer you will have to have connections from every neuron to every neuron. And so what this would mean is that you would have as many as 3072 times 4074 connections, and this is in fact slightly bigger than 14 millions. So what this means is that if you go about it in this way, you will need to have, just for the first hidden layers, you will have to have a little bit more than 14 million parameters that you need to estimate based on the data. And that's going to, amplify even more as you have more filters applying to your data and you implement them through additional hidden layers. Now, the point here is that, as a matter of fact, these parameters, these 14 million parameters in this first hidden layer, they are not independent from each other. And the way to realize this is that we really only want to implement 6 filters. And these filters, they are fixed, I mean, each one of them is a fixed transformation. And so what this means is that the computation done by this hidden layer, the computation done in each one of the neurons in this hidden layer, in fact, is very similar to what the other neurons do. Because all of these computations correspond to just, 6 fixed transformations. So what this means is that all of these multiplications that are done for this neuron and for that one and maybe for many others in this hidden layer are in fact exactly the same, and they are using exactly the same weights corresponding to whatever we want these filters to do. So thinking about it in this way, you realize that in fact we do have 14 million parameters, but many of them are in fact shared. So the number of independent parameters, the number of parameters that we really have to estimate could in fact be much smaller depending on how we design these connections. And finally, the last point I want to make is that these layers, in fact, in practice, if you think about this idea of having filters, kind of detecting simple patterns in the input coming into this layer, the idea is that these layers in fact are sparsely connected. In fact, you don't really even need so many connections. In fact, you can set most of them to be equal to 0. And the reason why this is true is because these filters, if you think about the applications in image processing, could, for example, look for a specific pattern. Let's say it looks for a vertical edge. And whether in a corner of a picture, maybe somewhere here, there is a vertical edge, is just a function of a few pixels that come into this corner of the picture. It certainly doesn't depend on the pixel coming in most of the rest of the picture. So what this means is that the computation done in the hidden layer of this neural network, in fact, in practice, if we think about applications done in image processing and these transformations done with the idea of filters, in fact, they only depend on a small number of inputs from neurons from the input layer. So that means that we have in fact quite a small number of real connections in here. Most of them are in fact equal to 0. And for example, the way this is done with convolution, and I will come back to this and discuss it in all details, but I just anticipate here that one filter could be seen as a transformation done via a, for example, 5x5 matrix. So a filter would be just a 5x5 matrix, and the way this would go would be that we would implement a certain operation between this input image, and the operation is going to be that of a convolution. We have 5x5, but in fact you will see that we will need in fact a 5x5 for each one of the channels or each one of the layers in the previous layer. So in fact, in practice, we will have 5x5 by 3. A filter would be just such a tensor, 5x5 by 3. And as usual with neural networks, we would have this addition of a free term. So in addition to these filters, we would have one extra parameter, which is going to be additional, just in the same way that the computation of any neuron is implemented also in fully connected layers. So what this means is that we will implement this with each filter is going to be implemented through a data set consisting of this many parameters, which is in fact exactly 76. And because we have 6 filters, so in a CNN we would need only 6 times 76, which is 456 parameters. And And this is just for the first hidden layer, but the difference between how many parameters we would need in this case, 456, and more than 14 million parameters in the case of a fully connected network is really drastic. And this lays at the very foundation of the motivation why it makes sense to go for convolutional neural networks. They are conceptually simpler and they have drastically fewer parameters than the fully connected networks, and as a consequence of that, they are going to converge faster and they are going to need far less data to train than a fully connected network.